Hello, everybody. Welcome to this new live event organized by the Magic Telescopes and this new series of Meet the Magicians. Who are the magicians? We are part of this international collaboration, and our name, Magic, stands for Major Atmospheric Gamma Ray Imaging Cherenkov Telescopes. So, what we do is observing the universe, observing our universe, but not like normal optical telescopes or the telescopes that you maybe have heard about. Our telescopes are special because they observe very high energy light, which can be detected only with this very special structure that you have just seen. So what we do is not observe directly this very energetic light, but we
It's electron positron here.
but we reconstruct this light from the shower of particles that are created when the light comes to our atmospheres. So we study in a very special way this very high energy emission, and then we can learn something about the most energetic events in our universe. So usually we can observe different kind of galaxies, different kind of celestial objects, and we even monitor some sources that are kind of our friends, so we know where they are. We know that they emit very high energy gamma rays, so we are ready to check what is happening in those distant sources. But sometimes there are events which are very unpredictable. They are not associated to a special source. We don't know where they are coming from. And these very violent and energetic explosions are so unpredictable and energetic that we call them transient. It's something that is very, it can happen suddenly, and it needs a special dedicated study. So when we have a transient and gamma ray bursts are the most mysterious transient that we know so far, we need a special crew of magicians to study them. So who you gonna call? We call our gamma ray bursters. There is a kind of a quite, yes, you can see them. The other side. We have many people which are gamma ray bursters in our collaboration, but today we will present three of them to you. They are young researchers working in magic. So let me introduce to you Alessio Berti.
Hi, everyone.
Hi Alessio. Alessio is working now in INFN, l'Istituto Nazionale di Fisica Nucleare in Torino. And then we also have with us Elena Moretti. Elena, she's another young researcher in magic. And then we also have with us Koji Noda, another magician, expert in gamma ray burst. And Koji, in this moment, is in Japan. So we tried to put together magicians from different time zones. And okay, we hope it will work also in the future. It's difficult to arrange live events with people coming from different time zones, of course. Well, okay, so let's start now to talk about these very special and unpredictable, mysterious events, gamma ray bursts. Let's start very simple. What are gamma ray bursts? I will ask this to Elena. Elena, please tell us, what are they?
So hello, Marina, and hello, everybody connected. So gamma ray bursts, as you said, are transient and they are explosions. So they happened serendipitously in the universe, in the far, far universe. And they are connected, most likely, with the death of a massive star. We can see here in the video, there is this star. It explodes at the end of its life, and then a jet emerges. These are called long gamma ray bursts. There are also another kind of gamma ray bursts, which are called the short gamma ray bursts. And these ones are connected to the collapses of two neutron stars that collapse into each other, and they still have a jet emerging. Now we see in this other video that when blobs of plasma, very hot plasma, are emitted from the star inside the jet, we can see here that some blobs collide with each other because they have different velocities. And in this case, when they collide, they emit high energy light, so giga electron volt light, or also kilo electron volt light. This is what we call the prompt phase, which is the most rapid one and very, very variable. It can last about 100 seconds. While later on, these jets collide with the interstellar medium. We see them at the end of the jet. And there we have the emission of other kind of lights, from radio to optical, UV, and so on. And now we know also very high energy gamma rays, so very high energy light.
Okay, so I understand that they are very special event, and the energy that can be released is extremely high. But I would like also to ask Koji something. These gamma ray bursts, they are detected. Okay, they started to be detected in the X-ray, in the gamma rays, of course. But why is so important to have them at very high energy, very high energies?
Hello, can you hear me? Yes.
Yes.
Yeah. So as Elena told you, there are already gamma ray emissions in giga electron volts or even less, so mega electron volts or kilo electron volts. But since decades ago, astronomers already detected the gamma rays in this giga electron volts energy, gamma ray of this energy. But there were a lot of mysteries in these energy regions. So, for example, just this emission, so gamma ray emission itself, the astronomers really didn't know why these gamma rays are emitted. And also, on top of that, the time of this gamma ray emissions are really mysterious. So the main part of the gamma ray burst, after this main part of the gamma ray burst, so this giga electron volt gamma rays are emitted a few minutes later than this main part, and this delay of the onset of these high energy emissions were really unknown to astronomers. So to understand, or at least to get some possibilities of the possible mechanism of these emissions, some more energetic, so more higher energy of gamma rays are really important to detect by our astronomers. And to do this, our telescope are really optimal to get these high energy events. So, and actually, we can, if we can detect these high energy events, we can get a lot of information other than this giga electron volt energy. So if we can get the thousands of higher energy, like tera electron volt energy, we can get a lot of information. So that is why, this is the reason why we really wanted to detect gamma ray in these high energies.
Yes, and we wanted to detect a gamma ray burst with magic very badly. It was something that we were trying to do since many years. And then after all this preparation, because we wanted really to catch one of those very mysterious events, Then after a year of preparation, 2 years ago, finally, we were able to detect our first gamma ray burst. And this is why today we are having this event, because today is the second anniversary of this huge discovery for our collaboration. And yes, of course, we have also scientific papers that we published, because in the community it's important that we give also our part in the publication of results. But there was a really huge preparation in terms of not only hardware, but only in terms of people producing the software and make this happen. So I think now for the following question, the best person to reply is Alessio, because Alessio started to work on gamma ray burst when he was a student, a PhD student. And he was very sad at the beginning because he was studying this very important topic, but there were no data on this gamma ray burst that he wanted to study. So Alessio, tell me, why is so difficult to catch a gamma ray burst with our telescopes?
Okay, so first of all, hi everyone again. So yeah, you are right. Detecting a gamma ray burst is quite challenging for us. So as both you, Elena, and Koji said before, the gamma ray bursts are really sources that last a few seconds and then basically they are gone. So what you need to do is to try to follow them up in a very fast way. And as you mentioned, the MAGIC was designed from the very beginning, so more than 17 years ago, to be able to move very fast when there is a gamma ray burst alert from satellites, which usually detect at least one gamma ray burst per day on average. And they send us coordinates of this gamma ray burst so that telescope like MAGIC can point to the coordinates of a gamma ray burst. And so what we have a software which receives these alerts, check the coordinates of the gamma ray burst, and if it is observable from the MAGIC site, then the telescopes are automatically repointing in a fast way towards the coordinates of the sky coordinates of the gamma ray burst. So maybe we can see a video of the telescope moving in the so-called fast mode or gamma ray burst mode.
Now.
Exactly. So this was a test done during the day, but you can see now that the telescopes, which are really quite heavy, 70 tons per telescope, here they move at around 7 degrees per second. And so it means that in few tenths of seconds, they can do a full turn if the coordinates of the gamma ray burst is, of course, in the opposite direction with respect the telescopes were pointing before. So there was a lot of work done by many people in order to make this automatic procedure very reliable. So it's not only the fast movement, which the thing that you can see and can be impressed by, but it's also making sure that the data taking on the gamma ray burst position is indicated correctly. And yeah, basically that's it. So maybe we can also see another picture where we have the whole light curve of the GRB, in which we can also see basically yes, that one, not the other one, please. So we can also see basically all the satellites that are basically the instruments that give us the alert and the coordinates of the gamma ray burst, and then all the other instruments that starting from this position, so not only MAGIC, but also the optical telescopes, receives this information, then they point to the gamma ray burst to understand what's going on there. So it's really a huge effort by many collaborations, not only MAGIC, of course. So it's really an international effort in trying to understand what happens in gamma ray bursts.
Yes, it was very great to finally detect gamma ray burst. But these events are very difficult to be detected. So we were able to detect the first one 2 years ago, and it passed a lot of time because we could detect another one, right? So now I wanted to ask Koji about the discovery of a new gamma ray burst that happened. Okay, because we have published 2 important papers on the gamma ray burst that was detected 2 years ago, but now there is another paper, scientific paper, which is just published by Magic, which is talking about another gamma ray burst. So, Koji, you were leading this paper. So, what can you tell us about this other gamma ray burst? What was some difference with the first one that we detected, for example?
Yes. Yeah. Yes. As Elena told you already, there are types in the gamma ray burst. And then the one we have been talking is the type called long gamma ray burst, and the one now the other one I will be talking is the short gamma ray burst. And this this guy what actually happened in 2016. So this itself is older than the one 2 years ago. But after 4 years, finally, we have published this paper. And this is very interesting because of the difference in these types. So as I told you, the different types has different origin of the star, and also this type, so called short gamma ray burst, we know less than the long gamma ray burst. So if this gamma ray high energy gamma ray emission from this type of gamma ray burst is really a general one in this type, then this will be the another big discovery. So I think this paper is also very interesting.
Yes, we are in the meantime in our backstage. Alicia and Julie are sending as a comment in our live stream these articles that we were talking about. 2 articles were published on Nature, and this also recent article that Koji was talking about. We will maybe send also later the links to the archive. The archive is the public container in which we store our works, in case you don't have access to the page of the journals. Okay, so also very recently we have detected another gamma ray burst, but as you can see from this discussion, it's very, very difficult to detect them. So every time we are able to do it, this is not only thanks to our researcher right now, but is also thanks to the people that worked on make this hardware so light, so the telescopes can move so quickly. Then it's also about people connecting alerts and be ready when there is an alert from another telescope immediately to move the telescopes. And this is not so trivial, because we receive coordinates, as Alessio was saying, and then these coordinates has to be put in our telescopes in an automatic way. Because can you imagine one person that is trying to insert new coordinates to find a new source, and be as quick as possible? It will take too much time. So it's important to make this automatic. So there is no person trying to type in a rush, but the telescope that go automatically to point in that position. Okay, so we always talk about our publications because for us it's very important to publish our results. And so we always show off about that. But I would like also to ask something about it to our gamma ray bursters about this experience of being gamma ray bursters. So I'm sure that all of them have particular stories about it, but I wanted to ask Alessio first. Alessio, you have a lot of stories about being a burst advocate. What is that?
So yeah, basically, as I said before, when we receive an alert of a gamma ray burst by some satellite, so the telescope repoint automatically. But what happens in the control room where we have the shifters who are taking the data of MAGIC is quite shocking for them, because there is a siren, a very high siren sound.
Yes.
And the screen becomes red and something like that. And so yeah, you cannot really miss that there is a gamma ray burst alert that is going to be observed. And so what happens after this first moment of shock, let's say, for the shifters, usually what they do and what they should do is to call the so-called burst advocate. So the burst advocate is one person who usually for 2-week shift. So there are these shifts of 2 weeks duration. So in these 2 weeks, there is one person called the burst advocate who is called by the shifters during the night when there is a gamma ray burst alert. And the burst advocate basically has the duty to follow the observation of the gamma ray burst, check if the data taking is going fine, checking the information of the gamma ray burst to see if it's an interesting gamma ray burst and if it is the ability to be detected by MAGIC. And so, yeah, burst advocates have to be, usually they are called during the night. So they are woken up by the shifters, and usually sometimes it can happen that they have take some decision fast when they woke up maybe at 3 in the night. And so it can be quite a difficult job sometimes when you have maybe not too much information and you need to understand what's happening and you just woke up. So, but yeah, so yeah, with some experience, then basically you can cope with this and take the right decisions during the night also.
Yes. So it's a very hard work, I have to say, because you need to be ready, and
you need to be on call. So
yes. Okay. Very good. So I would like also to ask somebody else about this, because all the people which are working on gamma ray burst and transient, they are burst advocate in turn, right? And they all have nice stories about that. So Elena, do you have some direct experience with with being a gamma ray burst advocate?
Yes. So yes, as Alessio was telling you, so there is one part that happens at the telescope and one part that happens in the house of the poor gamma ray burst advocates that are called in the middle of the night from the shifters, and they are woken up and told, we are observing at UB, is everything fine? Shall we continue to observe? But actually, another part that I'm involved personally, and I was very surprised that it happened, and somehow by luck it happened, when we detected this GRB 190114. I was actually there in La Palma. I was not part of the shift crew of MAGIC, but I was part of the commissioning crew of our big brother, bigger or smaller or younger, and the shifters actually called me because it was about 9 in the night, and told me, are we doing a test with the GRB? And I said, no tests, because sometimes we test the procedure and we test the crews. And they told me, then you should come, because we seem to be detecting a GRB, because they could see signals coming from a GRB, and we normally, yes, this one, and we normally are, it doesn't have anything. Here you can see a little bit, this S stands for significance, so it means how well we see the signal above the background. And here you see 11 in one and 8.6 in the other, which means we saw it very, very clearly. And this was, you see very few seconds, it says above 73 seconds after the beginning of the detection. Actually, this was the picture that they sent me and told me you should come. And I ran towards I was in my room, but I ran to the Magic Counting House and saw this thing happening, and I was super duper happy. Marina, we cannot hear you.
Yes, sorry. And Elena, I wanted also to ask you something about the first Nature paper that was published, which is named the electron emission from the gamma ray burst. And this gamma ray burst is called the GRB 190114C because it's the date in which it was discovered. Now, since you contributed a lot to this paper, I wanted to ask you something about it. Do you maybe have a copy of this paper that you can share with us, or should I share it with you?
I think it's better if you share it.
Okay, I will do that in a second. I will ask the Backstage to send me the link, so I can open it directly, because this, from this first gamma ray burst that was detected, we could publish 2 papers on the journal Nature. Why 2? Because in one paper we focused more, right, Elena, on the general event, and then we also published another paper which was about the multi-wavelength aspect, right? So while I find the link to the paper, can you please, okay, I got it. Thank you, Alicia and Julie in the Backstage. Okay, so I can share it with you. Why it's so important to have also multi-wavelength data. But okay, first we have a look to the article and then we go back to this multi-wavelength thing. Okay, I will share.
So if you want, I can start a little bit explaining why we published 2.
Yes,
so first of all, we decided to have one only explaining, as you said, the detection. So how we managed to get the detection, how it looked like, our signal, and start to draw a little bit the properties that we could understand of this kind of gamma ray burst, of this type of this event, from only the data we got at tera electron volt. So only the data we got with MAGIC. And this was the publication we got with the full collaboration, MAGIC collaboration. And this explained only the aspect of our detection, that is already an important detection, because it's the first time that we could detect at this energy, with this kind of detectors, the emission from gamma ray burst. So this was the first paper, while the second paper, as you said, is called the multi-wavelength paper. So it does an analysis of different data sets, from radio to our own data set, which is the highest energy one, with all the energies in between. And these data come from different type of experiments, as Alessio before showed, the light curve, which means the counts or the events we got as a function of time from this event. Exactly, thank you, from the Backstage, Julie and Alicia. So you see here, every color is a data set from a different experiment. And so we collected in the second paper all this type of data, and we tried to make the bigger picture, to draw to understand the properties from many point of view of the same object. So to reconstruct the puzzle that we got piece by piece in different wavelengths, and reconstruct it in a single picture by putting together all these pieces.
Fantastic. So this is something very important to do, to put the data in context also with the other energies. So I see there are already other questions from the public, but first I wanted to cover a little bit more about the Nature paper, okay? And then we will dedicate some time just to answer to the questions from the public, if it's okay. So about the first Nature paper, this one is, the first one was not in multi-wavelength. So we had only very high energy gamma rays and gamma rays in general. Why we wanted to do this? Because in the first paper, we just focused on this event itself in the gamma ray. They are called gamma ray burst. There is a reason why. The gamma ray emission is typical from this very unpredictable object. So Elena, last question to you, and then I will skip to the others. So I will try to share my screen again to show this first Nature paper and one picture for it. Okay, just a second, because I need to switch between windows. Okay, so here I think you can see this, which is figure 1 of the Nature paper. Elena, just explain to us what do we have here and why, and this is just a summary of this peculiar gamma ray burst without the multi-wavelength discussion, right? Can you explain to our followers what is this about?
Sure. So this first picture, this first plot, it shows the light curve. So is the number of events. Actually, here is the flux that we collect as a function of time. You see in the x-axis we have time, and in the y-axis we have flux. So you see here we have a very high flux at the beginning, and it slowly decays. It shows our signal, basically, that we could collect at that moment, and it lasts for about 30-40 minutes. So we could observe this kind of signal only for a very short time, so 30-40 minutes. Normally, with the other sources at this kind of energies, we can see them if they are steady, we can see them every day. They continuously emit, and we can continuously detect. If they are flaring, like active galactic nuclei, they flare only for a short time, like days. So we could collect the data of this flaring period only for days. While here, it's even faster. So it takes even less time to give us a very high flux, first of all, and to give us the detection. So, but on the contrary, the problem is that we cannot be late, because you see, after 40 minutes, we cannot see it anymore. So here in the, thank you, Backstage, here we see almost the same picture, but put it in a different context. Here we have it compared with the beginning of this event, with the gamma ray burst, the one that we are talking about. That is showed here in gray, as detected by another detectors that is called the Swift BAT. So you see, there was a first very active period emission that is called the prompt, as I said before, and then a slowly decay phase, which is called the afterglow. So after more or less 60 seconds, magic could repoint to this event. In the meantime, it got the alert, moved the telescopes, as Alessio showed us before, and then we could start to collect the data. And as you can see, the red markers are what we could observe, what are our flux in photons, so one by one, of the signal that we could see of this GRB. Why it's so important to see it in this context? Because you see, in 100 of seconds from when the star explodes, okay, we can have already emission at tera electron volt, which is very high energy emission. And while active galactic nuclei, for example, cannot do that. They do it in millions of years. They build up the jet and then they emit at this energy. While this super powerful events, the gamma ray burst, they do it in 100 seconds, even less. So they are super explosive and very, very, very energetic, like a Ferrari. Yeah. Or even better, a McLaren nowadays, no?
Yes. Okay, thanks. Perfect. And okay, I'm sorry, before I interrupted the question from the public, but maybe I should have, okay, it was not a critical question, so maybe we can answer right now. I can let Koji answer, okay? Elena, if it's okay for you. Okay,
absolutely.
This was the question. Which was the nature of the first detected gamma ray burst? He or she wants to know if it was long or short. So
yes, if this first means this one, the 2 years ago, this was a long gamma ray burst. Yeah, and as Elena showed this light curve, this bright part is just 20 seconds or so, but still longer than the type called short gamma ray burst. Yes, and what I told is that 4 years ago, this was a short gamma ray burst.
Okay, so it's weird to speak about short and long when anyway all these events are very are very quick for us, right? Okay, so there is a lot of things going on trying to interpret how this emission is. What is the emission mechanism of this gamma ray burst? It's still very mysterious. We have some processes that could happen, and there was briefly mentioned from all of you, and maybe if there is time, we can also try to go a little bit more deep in that. But for now, I think that our followers are also interested. Okay, they are for sure interested in the physics behind these very mysterious processes, but they also want to know something about the life of researchers. So here our guests now are very young researchers in the sense that their scientific career is still young, we can say, but also in terms of age they are young. So I just wanted to ask you some questions about their life as a researcher. So Alessio, what can you tell us about your life as a researcher now, or maybe also as a PhD student, since you were PhD student, PhD candidate since a few months ago, right?
Well, actually, years ago, because now I got my PhD 3 years ago. So,
oh my God, I'm a bit.
Yeah, time flies, I think. Yeah,
many months. So, okay.
Yeah. So yeah, as regarding the PhD life and linked to the gamma ray burst topic, I would say, as you said before, it was not an easy topic, I would say, within MAGIC, because, as you said, we tried for so many years to get one get one GRB detected, and actually we got another one in last December. So it seems that now that we detected one, now things are going, let's say, somehow differently to what happened in the past 15 years. So it seems now something has broken, let's say, and now we are really detecting more and more gamma ray bursts, and that is not good only for us, but for science in general, because we can understand better these kind of sources. And so, as I was saying before, yeah, it's not an easy topic, and so sometimes it can be tough to work on this, because okay, you observe the GRBs, but then you don't have the detection, and so yeah, you would like to contribute to the study of these sources without detection, but you cannot do it because you don't have the detection. But yeah, the thing is that at this point, when this happens, is that you don't have to let it go, and just be strong and go on and keep it up, because yeah, in science it happens many times that you are trying to prove something, and you cannot. Yeah, maybe you take years to prove it, like for GRBs. So we didn't really know that if we could detect a GRB, but at the end, yeah, after many years of trials, of testing everything to be perfect, in order to follow up automatically, in order to have basically no failures in the analysis, in data taking, everything, and so on. And at the end, you can reach your goal. So I think that the point is, even if can be tough times in research during the PhD, but also in the other steps of the career of a researcher. But yeah, somehow one has to keep going if one believes that the goal can be reached somehow, and that's what we did basically. Yes. So when we detected the GRB, finally, it came basically as a surprise, as also Elena said. But yeah, at the end, yeah, what came out of it, not only from the personal point of view, but also to what we could deliver to the community, was really great, I would say.
Yes, this event is, the first detection was very important, but in general, all gamma ray bursts are very important, because you want to understand how they work, how this emission is created, why you have such a sudden explosions, but you can also use this data for other fundamental physics study, because when you have an event which is so particular, then you can, for instance, test Lorentz invariance violations and other topics which are connected to the physics of this object. So yes, being a PhD is a very difficult phase of a researcher career, because it's a situation in which you are still a kind of a student. You are trying to start your academic career, and so working on something that you still don't have seen can be very frustrating. But in your case, this worked well, because at the end, the gamma ray burst.
And also for others who came after me, yeah, I guess so.
Exactly, but I hope also dark matter PhD students can soon have some dark matter evidence. But okay, I don't want. I cannot talk about this right now. But okay, there is not life only life of PhDs, which is particularly delicate. Also, we have. I wanted to ask Koji about his experience now. Koji. How is working and trying to put everything together also with the family in this very strange situation right now?
Yeah, actually, I have 2 kids, and the second one actually came after this year, so everything is special. But anyway, in general, I think this life of the researchers are very flexible compared with other jobs. Probably I don't experience, but yeah. So for example, if the kid have some cold or so, I can stop working. This is easy, relatively easier. So I think this is good. This is a good point of the researcher for the life with kids. And for me, the one kind of annoying thing is the time difference, because I'm now living in Japan, and relatively these colleagues in Magic Collaboration are mainly in Europe. So normally the meetings are held in the late afternoon or evening in Japan. So this is a bit annoying to me. Maybe you know this life with kids. Normally, the time will be shifted to the morning. So if I work until the late evening, then the next day will be disaster. So this is one bad thing for the research. This time zone. But actually, there is one good thing, very special for this magic and gamma ray burst observation. This is as Alicia told, this is a burst advocate. So I'm also working sometime for this burst advocate. And because of this time zone shift, so the midnight or later than midnight in Europe means the very comfortable morning in Japan. So actually, if the event happen in the very late night in Europe, then I can take care very in comfortable way. So actually it happened for some GLBs like this gamma ray burst, this 1901 also other gamma ray bursts. We had this kind of very comfortable situation in Japan. Not so comfortable in Europe means very comfortable in Japan. So I think that, in more or less for me, the life with family, but in magic and together with the colleagues in Europe, I think this is really happy situation.
Yes, it's very difficult to conciliate with time zones, and now magic will be part of a bigger experiment with this, which is the Cherenkov telescope array, and there is even more different time zone to consider. And that is like going to have meeting all day and night is a bit confusing, but we will try to organize this thing. But Koji, we wanted to see your children, but we can't because it's too late. They sleep. Okay. Well, next time. They are adorable. Yes. Okay, and Elena. Also, I wanted to ask you something about your personal experience before we move to questions from the public, which are also very important for us. So, Elena, we know, everybody knows that there is a very clear bias in gender in the scientific community. We know about this. It's difficult to fix this. So we do little steps, but I just wanted to ask you, how do you feel about that? If you have some personal experience to tell us, if you have some advice for younger researchers, because you know at the PhD level there are a lot of women and everything is more or less normal. Then when you move to higher careers, something terrible happens. So you have some advice or some consideration about this, maybe?
I'm afraid I don't, but I can tell you my own experience. No, my own experience is that, yes, as you said, it becomes less and less of the female gender and the more of the male gender. So your colleagues start to be more and more male. But I think some things are starting to change, at least from the low levels, so from the bottom of the pyramid. And I hope it will escalate to the top, although the top is still very male dominated. It's not only my own opinion, I'm sorry, but it's statistics, so you can see it everywhere. Life as a researcher can be demanding. So you move a lot from country to country, and you have short-term contracts. And this affects a little bit also your personal life. So my best suggestion is to everyone who wants to do this kind of job is do what you feel like and what you really like, because the demands might be high. But if you are doing what you like, it's fine.
Yeah, it's also what I think in this moment. Okay, well, so we have a nice question from the public. I think we can focus on a question from the people. Okay, now, okay, what are remaining mysteries in long GRBs? A lot. Can we expect very high energy gamma rays in prompt phase? Okay, who wants to answer to that? Maybe you can share. Okay, Elena, please go on.
Sorry. I really like gamma ray bursts.
Go on. No
and I'm a nerd after all. So yes, the second part of the question is actually one of the remaining mystery. If there is such kind of emission, very high energy emission in the prompt phase, as you perfectly noticed. We saw it only in the afterglow phase and not in the prompt phase. Maybe because we were a bit slow, although not too slow. But this is a fantastic challenge to be on time for the prompt phase and be able to detect the gamma rays in very high energy emission. So here you see in the cartoon again of how it's formed. So to see the emission, not only when it is in the final stage, when the jet hits the interstellar medium, but also when the blobs interact between each other. And if that happens, it means that it's even more powerful than what we thought up to now. So this is very, very important. And other mysteries are, for example, what is the structure of the jet? You see, this cartoon is somehow how we think it works, but we are not very sure that this works like this. So the structure of the jet, it's also an important matter for us. Then there is, of course, the question of the progenitors. We know now that after the detection contemporaneous of gamma ray burst and gravitational waves coming from a collapsing neutron star merger, so a binary of neutron stars that collapsed, that one of the progenitors, so one of the mechanism to form a gamma ray burst is actually this collapse, but we do not have the final proof, the smoking gun for the long gamma ray burst. So for the short we have, for the long we still have, and this is another mystery. And then there are a lot of other mysteries that we still don't understand how it works inside the jet, how they are produced exactly. We know there's some mechanism, of course, but we don't know exactly if actually the blobs are interacting with each other, if there is another kind of mechanism. This is still open for many years, most probably. Marina, I think we cannot hear you.
Okay, sorry. There is another, thank you for your answer. There is also another question from Tanjiro. Who wants to answer to this? It's about the first gamma ray burst in 15 years, the second one, 2 years, next one will be this year. Okay, who wants to reply? Okay, Koshi wants.
Yeah, actually, this is a bit difficult question to answer. If we will talk about only the luckiness or statistics, but I want to talk about the future, not actually very near future experiment. So that there is another collaboration called Cherenkov telescope array. This is very similar to this MAGIC telescope. And actually, these very similar telescopes are under construction next to the MAGIC telescope. So, and of course, there are a lot of improvements in these telescopes. and especially if we will talk about the detectability, so this speed to the point to the object is faster than the magic telescope. So if this works very well, we expect a lot more gamma ray bursts, or not only gamma ray bursts. Actually, we are trying to see many more other objects as well. So yeah, this is probably good answer to close to the end of the question.
Yes, I think.
Yes, thank you. Yeah, maybe better to say this is the artistic view. So that these two white telescopes are magic telescopes, and these red telescopes are artistic view. But among these telescopes, one is already constructed, and the others are under construction. Yeah.
Okay, and there was. Thank you, Koji. There was also another question from the public, and it was here. Yes.
I think I can answer.
Okay, Alessio. So we said that we first read the question, right? So we said that satellites are able to spot 1 gamma ray burst per day. Do you think it will be ever possible to spot gamma ray bursts at an almost daily rate also for MAGIC?
I don't think so, just because if you take into account that GRBs come from different direction of the sky, and you need and the gamma ray burst coordinates needs to be basically above MAGIC, so visible from the MAGIC site, you will get that the alert that can be observed by MAGIC are basically few per month. So it will not be daily rate for MAGIC for sure. Unfortunately for us, of course.
Yes. Thank you, Alessio. Of course, Fermi can scan the entire sky every night. We cannot do that, unfortunately.
We have a very limited field of view, so.
Yes. It would be nice to be launched on a satellite, but we can do this. Yes, this is fair.
There is actually, there was an idea for, it's called GEMUSO, to have eye shower arrays detection from the space station, so looking down into the atmospheric, but it's not still yet working.
Yes, I have heard about it. Yes, this project. Okay, and we have another question also. I can't read the name. Sorry, I'm doing something. Okay, I can't read the name of our follower, but okay. They asked the burst can be produced by magnetar eruption. So is that expected to detected by MAGIC? And if MAGIC, any survey on magnetar? Okay, okay, Elena, please.
Sorry for elbowing my way out. Sorry. No, actually, maybe this question is connected with the press release that happened yesterday about the detection of a magnetar outside our own galaxy. And that we saw as a GRB. So it's the type of emission can be somehow recognized to be short, to be connected to the death of a massive star. To be connected in case of the short to the collapse of a binary system, or to the magnetar, as it was recognized for this event. So in the case of short in terms of duration, you see, yes, we saw it in terms of short, like what we think as short in sense of the progenitor, of course not, but In the terms of time of the prompt, yes, as it was this detection announced yesterday. Magic have a survey of magnetars? Not particularly. But this one was not a magnetar in our own galaxy. The one of yesterday was in another galaxy. So this was even much rare. And in any case, if in the case that this kind of magnetar eruption causes and triggers, as it has done in that case, the alert system of every of the satellites, Magic does follow it in the same way it follows the other alerts. So it doesn't distinguish actually if it comes from a real gamma ray burst or from a magnetar. The alerts come and there is no time, as explained before, there is no time to decide whether it's one kind of event or another kind of event. We just repoint and take data. We actually did not have any data for that event. I don't remember if we followed it. I think not.
No, I think we were not operational.
No, we were on the other side.
Pandemic. Yeah. No, but there was the pandemic, so we were not. And also, what I can add is that Alicia in the backstage is working on magnetars in Magic, so you cannot see it.
Indeed.
Yes, I was thinking that maybe Alicia, who is now in the backstage, can tell us something about that, because she's expert of galactic physics. Maybe Alicia, you want to say something about this magnetar thing? She's muted. I'm sorry that I put Alicia in the middle like that.
Now?
Yes.
Yes, Alicia, okay. We can hear you. Sorry to bring you in this way, but you are the galactic expert here.
Yeah, so I'm Alicia Lopez Oramas, and I work at Instituto Astrofísica de Canarias in Spain. And basically in Magic we have like a galactic program for searching magnetars inside the galaxy. Along the years, we have tried to see if magnetars can show some steady emission, not transient emission like the one we have been discussing here, but a steady emission coming from the interaction with the interstellar medium, for example. And in this case, we have not seen any gamma ray emission. And then we also try to search for this transient emission or gamma ray bars coming from these magnetars. So actually, we are looking for them, and as my colleagues were saying, when there is an external alert that we receive from a satellite, our telescopes automatically repoint and try to see if we can catch this transient emission from magnetars. So for the moment, we are still looking for them, but and I hope we can find them real soon. I go back to backstage.
Sorry, Alicia. Thank you. Okay. So, well, you can see there are also people working in the backstage, but they are. We do everything by ourselves. In Magic we have outreach. We have everything. We need to do it ourselves. Okay. Now there is a question which is more general. I could reply. I could answer if you want. So it's about, do you think the lack of females in higher position in science, a personal choice of females due to the transient nature of the job, or a cultural problem with male leaders of science facilities? Okay, Jim, this is very difficult to reply, because there are many factors, that make this happen. What we are sure, if there is the gender gap in the science community, because this is very clear from the data. But the reason why this gap exists is a mixture of different problems. It's probably the fact that the female were not, since many years, they were not included in these fields. And now they are starting to to be there. And so it's not easy for them to go from a simple student position to higher positions. But this is very difficult to answer because female researchers, they are very different between them. Some of them have children, some of them have not, some of them are interested in career, some of them not. So it's not easy to give a precise answer. Also, as researchers, we are not very expert in understanding this problem. We experience it, we try to learn about it, but there are experts which are working also in analyzing this problem. For sure, things I can tell you exactly. I think it's more about the society, which does not push women to be in science, but it's a very difficult answer. What do you think, guys? Do you have an exact answer for these questions? I think it's not easy to have just a simple answer, right?
I think there are many people studying these all these factors and trying to disentangle and trying to find a way. So yeah,
Yes,
I think
because,
an exact answer is really difficult. Yeah, sorry, Elena, maybe I interrupted.
Fine. My opinion is very similar to the one expressed already. It's a mixture of factors. There is, it's been somehow proven with several experiments, also the bias into deciding whether a woman gets a position, or a woman or someone part of a minority gets a position or not, even at postdoc level, or gets a grant or not. Normally they are pictured as not independent enough, and so not able to take decision, or less secure or less expert in a field. But there is surely also another mixture of things due to the lack of women in the committees, or the lack of minorities in the committees, because there are other studies showing that committees try to select something that is similar to the members of the committee, and so not choose the other side, so the minorities. So yes.
Yes, there is like a problem in choosing this career because it's difficult to go through, and another problem which is that already there are not enough women inside. I mean, there are a lot of problems overlapping. What we do in MAGIC is try to understand this. So now we have diversity, equity and inclusion task force that we created inside MAGIC. So it's composed by us again, because we want to learn what we can do to make this better, but also we want to understand why this happens and what can we do, because we are inside this problem. We see there are not enough females, but this is not easy for us to understand exactly why, because cases are very different from each other. Like, for instance, if you have children and you are not supported, then you say, okay, I can't do this job, bye. But then what does it mean? There are a lot of women that don't have children, and then they have different problems. So it's something that has to be fixed in a lot of levels, for sure. Okay, so I would say we will cover this problem in the future in some other... Jim, yes. Well, you don't have to be concerned, because we are already fighting, and when your daughters will be in science, the path will be more easy for them. So we will cover this problem maybe in some live, because it's something that is important for us. And not only gender gap, but any kind of minority issue. Okay, so I would say we passed 1 hour. We had a very nice chat between us. And I would like to ask to our followers, if they have other questions, they can just leave them in our social media and we will reply to you in another moment, okay? So I want to thank you a lot for participating to our live. I want to thank you guys, our gamma ray bursters. I want to thank a lot our backstage people, Alicia and Julie, which they did not talk much, but they were always ready to help and to moderate this event. So thank you, thank you all, and happy birthday, first gamma ray burst discovered my magic, and have a nice day, all of you, and a nice David, our best friend. Bye, David. And I wish you a nice continuation of the day, and if you are in Japan or in other time zone, a good night. Okay.
Thank you very much.
Bye.
Bye all.
See you. Bye all. Bye.